Welcome to an intriguing exploration of the laws of thermodynamics, the fundamental principles that govern the behavior of heat, energy, and entropy in our universe. These laws are not just theoretical concepts but practical tools that shape our world, from the workings of a refrigerator to the efficiency of power plants. Today, we'll unravel the mysteries of thermodynamics, delving into its key concepts, practical applications, and the broader implications of entropy. So, let's embark on this journey and discover how thermodynamics underpins the workings of the physical world. Thermodynamics is the branch of physics that deals with the relationships between heat, work, temperature, and energy. It provides a framework for understanding how energy is transferred and transformed in systems, from the microscopic to the macroscopic scale. Thermodynamics is essential for understanding the behavior of gases, liquids, and solids, as well as the processes that occur in engines, refrigerators, and other technological systems. Thermodynamics revolves around several key concepts. Energy, the ability to do work or produce change. Heat, the transfer of energy due to a temperature difference. Work, the energy transferred when a force acts over a distance. And entropy, a measure of disorder or randomness in a system. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transformed from one form to another. In the context of thermodynamics, this means that the total energy of a closed system remains constant. This principle is a cornerstone of physics, providing a foundation for understanding the behavior of energy in all its forms. Internal energy refers to the total energy of a system's particles, including kinetic and potential energy. It is related to the temperature of the system and can be changed by heat transfer or work done on or by the system. The internal energy of a system is a key concept in thermodynamics, as it helps to explain how energy is stored and transferred within a system. Practical examples include a gas compressed in a piston, where work is done on the system, increasing its internal energy and temperature, and an electric heater warming a room, where electrical energy is converted into heat energy, warming the room and increasing its internal energy. Entropy is a measure of the disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time, meaning that natural processes tend to move towards a state of greater disorder. Entropy is crucial in thermodynamics, explaining why certain processes are irreversible and why energy cannot be converted into work with 100% efficiency. Heat engines are devices that convert heat energy into mechanical work, and their efficiency is limited by the temperature difference between the hot and cold reservoirs. According to the second law, no heat engine can be 100% efficient. Some heat is always lost to the environment. This limitation is known as Carnot efficiency, which sets the maximum possible efficiency for any heat engine. A reversible process is one that can be reversed without any change in the system or its surroundings, while an irreversible process involves an increase in entropy and cannot be undone without some change in the system or its surroundings. Examples include melting ice, which is reversible, and burning fuel, which is irreversible. Understanding these processes is crucial for designing efficient engines and technologies that minimize energy loss. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum value. Absolute zero is the theoretical temperature at which particles have no thermal energy and are in their lowest energy state. This law has significant implications for the behavior of substances at very low temperatures and sets a limit on the efficiency of refrigeration and the feasibility of reaching absolute zero. The third law affects the behavior of substances at very low temperatures, influencing fields such as cryogenics and the study of superconductivity. It also highlights the theoretical limits of cooling processes and the challenges of achieving temperatures close to absolute zero. Thermodynamics principles are applied in various everyday technologies, such as refrigerators and air conditioners, which use the principles of thermodynamics to transfer heat from one area to another, keeping food fresh and homes cool. The refrigeration cycle, involving the compression and expansion of refrigerants, is a direct application of thermodynamic principles. Vehicles utilize the internal combustion engine, a heat engine that converts chemical energy into mechanical work, with its efficiency governed by thermodynamic principles, particularly the second law. Industrially, thermodynamics plays a crucial role in power generation, With the design and efficiency of power plants based on thermodynamic principles, whether it's a coal-fired plant, a nuclear reactor, or a renewable energy source like wind or solar. In aerospace, the behavior of gases and materials at high temperatures and pressures is critical for engineering aircraft and spacecraft that can withstand the extreme conditions of flight in space. Entropy is also a concept in statistical mechanics, where it is related to the number of possible microscopic states of a system, offering insights into the macroscopic properties of systems and the direction of spontaneous processes. In information theory, entropy measures the uncertainty or randomness in a set of data, highlighting its significance beyond physical sciences, influencing fields such as computer science and cryptography. Here, entropy quantifies the amount of information needed to describe a system, providing a bridge between physics and information science. In conclusion, the laws of thermodynamics are fundamental principles that govern the behavior of heat, energy, and entropy in our universe. We've explored the first law, which states that energy cannot be created or destroyed, and the second law, which introduces the concept of entropy and the tendency towards disorder. The third law provides insights into the behavior of systems at very low temperatures. Thermodynamics has practical applications in everyday technologies and industries, while the concept of entropy has broader implications in fields like statistical mechanics and information theory. By understanding these principles, we gain valuable insights into the workings of the physical world and the nature of energy and information. Thank you for joining us on this exploration of the laws of thermodynamics. The principles we've discussed today are not just theoretical concepts but practical tools that shape our world. Stay curious, keep exploring, and who knows? You might just discover something new about the universe. Whether you're experimenting with simple thermodynamic systems at home or diving into more advanced topics in physics, the laws of thermodynamics offer endless opportunities for discovery and innovation. Thank you for watching. If you're hungry for more knowledge, hit that like button and don't forget to subscribe. Your support is incredibly valuable to us.